Hello and welcome to the introductory video on diagnostic accuracy. Estimating accuracy of a test or a method is one of the most common problems encountered by pathologists. All of us are pathologists. We are diagnosticians. Diagnostic accuracy is very close to our heart. We have plenty of problems which come in our day-to-day practice. For example, is FNAC of the breast or any other tissue, lymph node, thyroid, salivary gland, lung. Is FNAC accurate enough? Are our reports accurate enough? Or is a certain immunohistochemical marker accurate enough to diagnose a certain disease? For example, is TTF1 accurate enough to diagnose lung adenocarcinoma in non-small cell lung cancers? Hematologists may think of other diagnostic accuracy problems. For example, is reticulocyte hemoglobin accurate enough to diagnose iron deficiency? For that matter, is ferritin accurate enough to diagnose iron deficiency? There may be other problems faced by laboratorians. For example, is my portable hemoglobinometer accurate enough to give hemoglobin results? So, for all these tests done, we need a method to be tested. The method to be tested is known as the index test. And we also need a reference method against which the index test is to be compared. For example, for FNAC, as the index test, the reference method may be histopathology. For reticulocyte hemoglobin, to diagnose iron deficiency, the reference method may be ferritin values. For any problem, we have to realize that statistics is not an end to itself. It is not different and it does not stand in isolation from the problem you are facing. It's an integral part of the problem solving method. Anything starts with a problem. You have to face a problem from which you frame a valid research question. Once the research question has come into your mind and you are clear about what you are to do, you come up with a valid design. Then you have a valid sampling and experimentation from which you select a valid statistical test and do a proper inference. So all of these form a part of a whole. Nothing stands in isolation from one another. Taking the example of a diagnostic accuracy study with breast FNAC, the problem may be, I do not know how accurate FNAC is in diagnosing breast malignancies. So, from here, the research questions comes out. Is FNAC accurate enough to diagnose breast malignancies when compared to histopathology? From there, a design comes out. It's a cross-sectional design. It may be either retrospective or prospective. From there, a proper sampling and experimentation is done on random or consecutive patients, preferably not a haphazard or convenient sampling, which is tested by both FNAC and histopathology. Then the proper statistical tests, sensitivity, specificity, PPV, NPV, along with the upper and lower confidence intervals. And finally, for proper interpretability, we also have to see how generalizable the results are. Now, we have just talked about the index test. We should remember that the index test should be described in a method which will allow reproduction of the experiment. Another thing about the index test is we have to be clear what sort of a variable it is. Is it categorical? Is it ordered categorical? Or is it continuous? An example of categorical index test variable may be IHC TTF1 positive and negative. An example of an ordered categorical index test may be FNAC report categorized as benign to atypical to malignant. An example of a continuous index test may be reticulocyte hemoglobin. So, we have these various forms of variables for the index test. For the reference test, we should realize that the reference test should be taken to be as accurate as possible and as close to the gold standard as possible. For all statistical tests, the reference test is usually assumed to be free of all measurement errors. Now, the reference test itself may be dichotomous. For example, disease positive versus disease negative. That's a very, very common scenario. Or it may be continuous. For example, hemoglobin measurement by a reference method. Now, why we are talking of so many types of variables? That is because the statistical test we choose depends on the type of variable. For example, in accuracy studies, if the reference test is dichotomous and the index test is dichotomous, we use sensitivity, specificity, PPV, and PV. If the reference test is dichotomous and the index test is ordered categorical, we use sensitivity, specificity, PPV, and PV, but at each cutoff. Or we may be using the ROC curve analysis. When the reference test is dichotomous and the index test is continuous, we use ROC curve analysis. When the reference test is continuous and the index test is continuous, we can use the limits of agreement method, which is very commonly used, or we may be using more complicated linear regression methods. So, it is very, very important to define the variables and have an idea of whether the variables you are dealing with, whether they are dichotomous, they are ordered categorical, or they are continuous. This helps in selection of the statistical test. Now, let us see the how to analyze accuracy studies in further detail. Let us take the example of a dichotomous index test and a dichotomous reference standard. An example may be, say, a diagnostic test reporting samples as either benign or malignant, positive or negative. It may be FNAC. Say, in the case of FNAC, in the example of FNAC diagnosing test as benign or malignant, for diagnosing malignancy, a positive test would be a malignant report on FNAC. A negative index test would be a benign report on FNAC. For the above example, the reference test would most likely be histopathology. In this case, a malignant report on histopathology would be classified as disease positive, and a benign report on histopathology will be classified as disease negative. Now, what are the measures of diagnostic accuracy? For diagnostic accuracy study, we should be quite clear. Accurate test should be accurately picking up disease positive cases and calling negative disease negative cases. This is the basis of diagnostic accuracy studies. So, one of the main measures is the proportion of disease positive cases picked up or called positive by the index test, the actual disease positive cases picked up by the index test, or the proportion of disease negative cases excluded or called negative by the index test. Besides this, there are two more tests which are used. The proportion of index test positive cases being actually disease positive, and the proportion of index test negative cases being actually disease negative. Now, these are given special names. The proportion of disease positive cases picked up by the index test, that is called sensitivity. The proportion of disease negative cases excluded by the index test is called specificity. The proportion of index test positive results being actually disease positive is called a predictive value of a positive test. Many people call it a positive predictive value or PPV. And the proportion of index test negative cases being actually disease negative is called a predictive value of a negative test. Some textbooks refer to it as negative predictive value or NPV. Now, for any of these results, in actually analyzing the data, cross-tabulation may help. What does a cross-tabulation look like? Cross-tabulation, you give the number of cases arranged in a table in a format which will give the index number of index test positive results and the reference test positive results, as well as the index test negative results and reference test negative results in a convenient, easy to understand format. In this table, we may see or interpret it as there are 195 cases which are positive by both the index test and the reference test. This is the true positives. There may be also certain cases which may be test positive but actually negative by the reference test. Those are the false positives. Here in this case, the false positives is 0. But in many cases, or rather I should say in most cases, we have some amount of false positives. Now we have the index test negative results which are reference positive. Those are, if it's reference positive, that means it is positive, but if it is called negative by the test, that's a false negative report by the test. Number of people over here, 4 cases were false negative. And test negative results, which are also reference test negative, they are called the true negatives. So we have the over here true positives, false positives, false negatives, true negatives. And in this case, the sensitivity is the proportion of actual positive results detected as positive by the test. So positive tests over here divided by the total number of actual positive or reference positive tests, that is 195 by 199 in this case, and that is 98%. Specificity would be dealing with the reference negative cases. The proportion of actual negative or reference negative cases excluded or negative by the test. In this case, all the reference cases were called negative by the index test. And in this case, the proportion of actual negative cases, which is called negative by the index test, is 100%. You have the predictive value of a positive test, which are all the index test positive cases, the proportion of all the index test positive cases, which is also positive by the reference method. Over here, it would be 195 divided by the sum of the values of the true positive and false positive. So that is the predictive value of positive test. In this case, since the number is 0 over here, the predictive value of the positive test is 195 divided by 195 plus 0, that is 100%. And the predictive value of a negative test, in this case, it would be the proportion of negative index test results which are actually called negative. These are the total number of index test results. What proportion is actually called negative over here? That is 44 divided by the sum of 44 and 4, that is 48. Over here, that comes to 91.7%. So cross tabulation may help in actually seeing conveniently the results. But are these numbers by themselves important? No, they are not. They are numbers taken out from a sample. There's always some error. The confidence interval, and that's why we need confidence intervals to interpret the data. But before getting the confidence intervals, we should be knowing and putting in our mind what good accuracy and what bad accuracy means. Now, for interpreting the results, we use confidence intervals. I've already told you that. But before that, we should have an idea of the accuracy values for a satisfactory test or an unsatisfactory test. For example, for a satisfactory test, we may say that FNAC should pick up at least 90% of the malignant cases. That is, the sensitivity should be greater than 90% and exclude 95% of benign cases. That is, specificity should be greater than 95%. We should have that idea beforehand. In this case, if the sensitivity is greater than 90 or is demonstrated to be greater than 90 by means of confidence intervals, and the specificity is demonstrated to be greater than 95%. If both these conditions occur, we can say that our diagnostic test is satisfactory. Sometimes we may also try to demonstrate unsatisfactory results. For that, we need to set up the cutoffs for unsatisfactory result. That is, we may say that a diagnostic test should be at least 80% sensitive and 90% specific. If you can demonstrate that it is less than 80% sensitive or less than 90% specific, that will make it unsatisfactory. Now, to demonstrate acceptable performance, I've already told you, we make use of confidence intervals. For acceptable performance, we use the lower confidence intervals. The lower confidence intervals should be greater than the acceptable cutoff. That is, in the first case, the sensitivity, the lower confidence interval of the sensitivity should be greater than 90%, and the lower confidence interval of the specificity should be greater than 95%. For an unsatisfactory result, the upper confidence intervals are used. And for this, the upper confidence interval should be less than 80%. And depending on the design of the experiment or the upper confidence interval of the specificity should be less than 90%. So, to demonstrate unsatisfactory result, we use the upper confidence interval generally. To demonstrate satisfactory results, we use the lower confidence intervals. We have already spoken about a dichotomous index test. What about an ordered categorical index test, which is actually quite common, especially in FNAC? In FNAC, we often have results or use systems in which we report in following categories: benign, onto atypical, which actually is interpreted as probably benign in many cases, onto suspicious of malignancy, onto malignant. And from benign to atypical to suspicious to malignant, all these categories carry a specific meaning. They actually show increasing risk of malignancy. So these are ordered categorical reports. The problem with ordered categorical index tests is there are many cutoffs we can use. For example, what should we call a positive index test? We can either use the cutoff shown by the blue line over here and call atypical, suspicious and malignant reports as a positive report. Or we can use a cutoff of the green line over here and call suspicious and malignant reports as a positive report. Or even more conservatively, we can use the red line over here and use just the malignant category as a positive report. What should we use? The solution to this is to do a diagnostic accuracy study for each cutoff and examine the results of each. In this case, for such a system of benign to atypical to suspicious to malignant, we will be having 3 results of sensitivity, 3 results of specificity, 3 results of PPV, 3 results of NPV, and from there we can see the satisfactoriness of each and every cutoff. Maybe we can find out which cutoff is most appropriate. However, many times we are called on and asked, let alone the cutoffs, I realize that such and such cutoff is satisfactory enough, but what is the overall accuracy of the test? To find the overall accuracy of the test, we can plot the receiver operating characteristics curve. Now, receiver operating characteristics curves or the ROC curve, that also comes in play in assessing the accuracy of continuous index tests. What is the ROC curve? The ROC curve is shown to the left. It is just a plot of the sensitivity on the y-axis versus 1 minus specificity on the x-axis. 1 minus specificity is also known as the false positive fraction. And you just plot the various points, join the points, and then join the points to the top right corner and to the bottom left corner. You get a curve which is known as the receiver operating characteristics curve. Now, over here, for the receiver operating characteristics curve, a very good measure of overall accuracy is the area under the curve. This area under the curve over here. Area under the curve may take any value from 0 to 1. Now, while interpreting the AUC curve, we should realize that the point of non-information is a AUC value of 0.5. Non-information is not 0. The closer the value it is to 1, the better the test. Also, the closer to the value to 0, the better the test. It is just the interpretation changes. For values of AUC greater than 0.5, it means that increasing values of the index test correlate with increasing disease probability. Okay, and for values close to 0, it means that increasing values of the test are negatively correlated with disease probability. Let us take the example of ferritin. As ferritin increases, there is decreasing probability of iron deficiency anemia. In that case, the area under the curve will be closer to 0. So, for AUC, we have to remember that the point of no information is an AUC of 0.5. Now, once we have talked about the various ways to assess diagnostic accuracy, either by sensitivity, specificity, or by ROC curves, it makes sense to see how it is done by a demonstration video. For this, we have a data set, the catacc.xlsx, and it is on this data that publication has also been done by some of my residents. The aim of this analysis would be, and of this paper was, to assess the accuracy of breast FNAC in diagnosing breast malignancies using the International Academy of Cytology Yokohama system. Now, for the ISC Yokohama system, we have to know that there are 5 categories: inadequate, benign, atypical, suspicious of malignancy, and malignant. Now, from benign to atypical to suspicious to malignancy to malignant implies an increasing risk of malignancy. This catacc.xlsx has 4 variables: the HCAT, which is the histopathology category, the reference risk category, coded as 0 as benign, 1 as malignant. Then we have the FNAC 2 tier, in which just the benign and malignant cases were kept. The other cases were removed. They were taken as missing data. They were removed from the column. The third column, representing the third variable, that represents all categories over the information about whether a patient belonged to the inadequate, benign, atypical, suspicious, or malignant category. All of that is given. Yokohama is just the same as FNAC_all, but the cases are coded numerically. It is given a value of 1 for inadequate, 2 for benign, 3 for atypical, 4 for suspicious, 5 for malignant. 2, 3, 4, 5, increasing order, reflecting the increasing risk of malignancy. Now, we have done the demonstration video using a free software called EasyR. EasyR is built on top of the acclaimed R statistical environment. It can be freely downloaded from a Japanese university website. It is made by academicians for academicians. It is free, cross-platform, and has an easy learning curve. There are other excellent programs as well, like Blue Sky, which is free, but it's not cross-platform, it's Windows only. Jamovi and JASP are both free, cross-platform, easy to use, but there's one difficulty: it hides the R console, and we need the R console in some cases, as we will see. And it's also my philosophy not to hide the R console, because once you get used to R, you get to do so many analysis which you just cannot do by any other software. Then you may also use StatsDirect or NCSS. The problem is both have a cost, even though they are low cost for academicians and they are Windows only and are proprietary, but they are excellent, easy to use programs. Stata and SPSS, I need not mention, they are excellent, but they are high cost. And SAS is free for academia, it is proprietary, it's the granddaddy of all statistical programs. The problem is it has a steep learning curve. In the end, taking the shallowness of the learning curve and the ease of use, as well as the width of tests which are present on the menu, we decided on EasyR, but you can use any software you like. I hope you found this video to be a easy stepping stone, and I hope this will make you understand how to do a diagnostic accuracy study better. Thank you.